Do you hear me okay?
Yes,
Are you able
okay.
to?
Works.
Okay, thank you, Thomas. I'm going to try to share my screen. I'm going to do a share. And here I go. Are you able to see the slides?
Yes, perfect.
Okay. Well, thank you very much. It's an honor to be here to my first IWMTS. I know a lot of work goes into it, and I think this conference may be the harbinger of the future of wireless in many ways. So Thomas, I was very delighted to be invited by you and to be part of the community, and I look forward to seeing some of the talks later today. Good morning, good afternoon, or good evening, wherever you are. I'm really excited to present this talk, which I call Wireless Cognition and the Tricorder, introducing the sub-Terahertz future. The term wireless cognition is one we began using about 2 years ago. And if you look at the meaning of the word cognition, it means to learn, to experience, to sense. And that really is what wireless is going to allow us to do on so many different levels. And I hope to motivate some of what I think are the most exciting opportunities and the future for our industry and for the frequencies that are above today's millimeter wave frequencies. Are you able to see this screen okay? This is the famous Star Trek movie set. This series, Star Trek, was created by a relatively unknown screenwriter named Gene Roddenberry in the early 1960s. And he got the company that Lucille Ball, a very famous comedian, a famous woman comedian, I Love Lucy, Desilu production company. He convinced them to air this new series on television in the 1960s. Many of us who are electrical engineers and astronauts who are over 40 years old likely have heard of Star Trek. On the left, you see Captain Kirk and with Mr. Spock, who's part human, part Vulcan, and then the Dr. McCoy to the other side of Captain Kirk, and you see Spock giving his very famous Vulcan salutation, the salute. But it's really interesting to see how Star Trek has motivated the entire engineering field. And just let's see a show of hands. We have 57 participants. I'd love to see how many people know Star Trek. If you can ring in, if you've ever seen Star Trek, this might bring back some memories. And I'm gonna try to launch this. I'm trying to launch this server. Let's see if it does it. Can you hear me now? Can you hear me now? Or?
Yes.
Okay, sorry about that. Well, I'm going to let everyone click the link themselves later. Anyway, this amazing show, Star Trek, has motivated so many engineers. And one of the fascinating things about Star Trek is that there was this device called the Tricorder. And the Tricorder was conceived to be in existence for the Starfleet Command, which sent Captain Kirk and hundreds of space missions around the universe, visiting planets and seeing if there's extraterrestrial life and civilizations. And the Tricorder was the science fiction prop, which was created in the original series in 1966. And the Tricorder had as its performance, as its main mission, 3 functions. It could scan, and it could record data, and it could do data analysis, oftentimes determining the health of someone, determining whether the civilization had been aging properly, finding foliage. It also used the Star Trek communicator to beam information back up to the Star Trek Enterprise while people were on the planets. And this key thing, this idea of sensing, recording, and computing, and I'm going to add communications to that, was one of the most exciting things about Star Trek to me when I was a kid watching it. And you can click these links later. I assume the slides will be made available. Yes, Thomas? Can you hear me okay? Hello?
Sorry, yes, slides will be available.
Okay.
Yeah, we will do that. Yeah.
You'll be able to click these links later. They're really, really exciting, and I'm really sorry I can't show them to you. They're fascinating. But I don't know if people can click on them at home and if it'll mess up their Zoom or not. Maybe we could try that. Maybe people could try clicking on the links just to see what happens. You want to try that?
Let's say I cannot copy it just from the screen, so probably that's not possible.
Okay. You can't see this link right here. You can't click that. Okay.
Yeah, I can't click by my own.
Okay, so you'll do it later. Anyway, this shows you actual working the tricorder in the series. It shows props that were sold, but this idea of sensing, recording, and computing, and I'll add communications, is really captivating in how they just show it in the show. On the left, you see the famous Star Trek communicator, which made a funny beeping sound when Captain Kirk or Mr. Spock opened it up to talk throughout the galaxy. And on the right, you can see the tricorder, the device which did this amazing sensing, scanning, computing. Together, these two devices were the key concepts that allowed Star Trek astronauts to explore the galaxy, save lives, narrowly escape danger, and do amazing things, which inspired a complete generation of engineers. By the way, this is a true story. Marty Cooper, who's credited with leading the cell phone development at Motorola, told me personally that the Star Trek series and the Star Trek communicator on the left motivated him to build the cell phone, and later the famous flip phone that Motorola made. So the cellular industry really came about by this amazing vision of science fiction on the Star Trek series with the communicator and tricorder. Now, I have seen in my lifetime a couple of real life examples of people being motivated by science fiction. Marty Cooper, I just mentioned, and the Motorola team, which got into the cell phone business. But also, I personally knew the inventor of the walkie-talkie, Al Gross. He was a personal friend of mine when he became a retired man into his later part of his life. Al Gross had invented the walkie-talkie in World War II, the 1940s, and as a young engineer in Cleveland, he had made this walkie-talkie that he's shown using. Made it with tubes that operated at VHF frequencies. He had made it using bakelite and materials that a young engineer named Jack Kilby had shown him. Jack Kilby went on to start Texas Instruments. And Al, with this walkie-talkie, had also made a very tiny wristwatch receiver radio that he had in his lab. And the author of the Dick Tracy comic strip, Chester Gould, met Al Gross in his laboratory, saw Al's tiny transistor, tiny wristwatch radio. It wasn't a transistor. They didn't have transistors yet, but it was this little receiver, a mock-up. And in 1946, Dick Tracy comic strip had the first wristwatch radio ever in any kind of science fiction. It's a very famous US comic strip. He was a private eye detective who saved people and caught crime. And he wore the first wristwatch communicator in 1946. Well, in 1990, when I was a brand new professor and I had just met Al Gross, I had given an interview to this magazine in 1990, the Virginia Engineer, and I talked about that someday we would have wristwatch radio. If you look at this bottom paragraph, if a person was wearing a Dick Tracy type of watch, one that is a wireless telephone as well, that person witnessed a crime, he or she could report it immediately. And I was talking about 60 gigahertz back there, which in 1990 people thought was completely ridiculous. So all of us working in terahertz now are working at frequencies that many people think are unusable or ridiculous. But in 1990, I was talking about wristwatch radio and millimeter wave frequencies. And of course, in 2015, we have the Apple Watch, and I suspect several of you have an Apple Watch or some kind of wristwatch device, whether it be a Fitbit. So from 1946, when Dick Tracy started wearing the wristwatch, to 2015, which is about 70 years, we've got this idea of it appearing in science fiction to actually being made and brought into our society. So the idea of a tricorder, something that can scan the human body or detect things or sense, basically conduct cognition, coming about in 2245, which is what the Star Trek series was written for, that time frame, is not so far-fetched. In fact, I hope this talk motivates the fact that we're going to probably do it a lot earlier than 2245. It may be in our lifetime, my lifetime. So this idea of cognition, let's take a look at the idea of cognition: sensing, learning, experiencing. And to do that, we need to first consider the human brain and how powerful is it. What kind of computer do we have sitting above our shoulders that God has blessed us with? The human brain has about 100 billion neurons, each firing at 200 times per second. This is the ultimate in parallel processing, the human brain. Each neuron is connected to about 1,000 others. And what that means is the speed of our human brain, what we do to compute, each of us has a speed that's about 20 times 10 to the 15th. In other words, our brain with its massive parallel processor, 100 billion neurons, each connected in parallel to 1,000 others, simultaneously firing, we're operating at 20,000 terabits per second. That's our data rate. The data rate of the bus of our human brain and how we think in real time is operating at 20,000 terabits per second. And the memory of our human brain, the access, each neuron has write access to about 1,000 bits, 1,000 neurons, which are storing information. Now, for simplicity, we'll assume each neuron is writing in a binary fashion. Researchers of the brain have found out that it's more than binary. It's probably tertiary or more. There are more states than just binary, but for simplicity, let's assume that those 1,000 parallel connected neuron from each neuron is a binary write. We have a storage of our brain of 100, basically of 100 terabits per second. We have a hard drive, or 100 terabits. We have a hard drive of 100 terabits, which is pretty cool. You can get terabit hard drives now. So if you think about how we think and how the human brain works, we're at 20,000 terabits per second with 1,000 terabit hard drive with instant access, 5 millisecond access speed. Now, let's look at what $1,000 buys us today. This smartphone costs about $1,000 without subsidies. And there's a processor in there with multiple cores in parallel, maybe running at 1 or 2 gigabits per second. Each core running can operate several instructions or several computations per clock cycle. So we have about 1 trillion computations per second that is at today's technology. That's what $1,000 buys. But if we look out to 2036, just 15 years from now, $1,000 will buy the computing capability of the human brain, 20,000 terabits per second. We're gonna be able to compute at the human brain level in about 15 years for $1,000. Everyone will be able to have a computer comparable to the human brain. Now think about this. What that means is the commodity computing will someday enable us to be able to compute in hardware at the same speed and memories comparable to humans. This is amazing. So can we wirelessly communicate in real time at speeds of the human brain? And I believe yes. In fact, let's look to wireless in 15 years. And this is why there's so much interest in machine learning and artificial intelligence. This is why all these big companies that are mining so much data are hiring so many engineers away from wireless communications or other areas. That's why the salaries are so big. The big companies realize that we are literally a decade away from starting to approach computations comparable to humans. So let's look 15 years from now, 6G or 7G. Can we reach wireless cognition? That is the ability to send data in real time to remote the real-time processing speed of the human brain. Well, this should make it very compelling, but it is. 10 gigahertz RF channels, let's assume. Let's assume we're doing 10 bit per second, 1024 QAM, which we do today in 4G and 5G. Let's assume we can get 1,000 times the channel capacity. Already on the roadmap for 3GPPs, 5G, we're at 64 times channel capacity with 64 transmitters and 64 receivers for massive MIMO. So going from 64 to 1,000 is only another factor of 16. So can we get 16 times more capacity in 15 years? I sure believe so, as you'll see why in a moment. So if you put all this together, it means that we'll be able to transmit 100 terabits per second. That is about 1/200th of the real-time processing of the human brain, easily, I believe, in 2036. And now if we could use 100 gigahertz channels, which may sound crazy today, but I'll show you why I think it's viable, we'll be able to transmit at 1 petabit per second, 5% of the human brain's real-time computing speed. And there may be other breakthroughs that come about beyond massive MIMO, new modulations, new techniques we haven't developed yet. And why am I so much a believer that we'll get there? We wrote a paper about it in 2019 in IEEE Access. But the bottom line is, I think we're going to see this because look at what's happening now in the development of wireless communications. We're already moving to terahertz and sub-terahertz, and also I'll show in a minute, it's very viable. We're starting to move to super wide bandwidth channels. Look at 5G today, the millimeter wave bands of channels of 200 megahertz, 400 megahertz channels. I mean, this is so far beyond the 30 kilohertz channels of the first generation analog cellular, or 25 kilohertz in Europe. We have extremely sharp beamforming. We're starting to use machine learning for handover, for connection, for beamforming, for bringing content from the edge. I mean, the bottom line is, with all the distribution and the build out of the back end of the network and all these gateways that are caching memory and caching content so much close to the edge of the network, it should be clear that as we move higher and higher in frequencies and greater bandwidths, we're going to be enable this data rate, which is able to start transmitting in real time communications, which is on the order of our human computational capability, which means we'll be able to remote energy and information at the rate that our brain interprets it and processes it. So hopefully this shows that we already have the recording, that is the memory, and the computing capability of the tricorder. Remember, the tricorder is sensing, recording, and computing and communications. So let's investigate the communications and sensing aspect of that tricorder, that magic device, which hopefully when you get a break, you click on these links because they're really fascinating. I did a lot of work to try to find how the tricorder was depicted in the Star Trek series, and it's very exciting. I'm sorry it didn't show up. So let's look at Nokia, already looking at MIMO and massive MIMO to try to get to 1 terabits per second. But I'm looking at hundreds of terabits per second to get close to the human brain real-time data rate. What you can see is as you increase the order of MIMO, massive input, multiple output, which becomes easier and easier to implement at higher and higher frequencies because you have a smaller form factor and much more directional antenna elements. Because of the smaller wavelength, you're able to get much more directionality and more gain for a given physical area going up higher in frequency. There's this myth that most of the world still believes, which is as you go higher in frequency, the channels get lossy. That's so wrong in general in free space. And while yes, brick and walls and trying to get through materials gets tougher, most things get more reflective. And as you go higher in frequencies, there really is not much more channel loss other than rain and ice, and I'll talk about that in a minute. So this myth that you somehow get smaller link coverage at higher frequencies is just that. It's a myth, because you're able to make up for the omnidirectional free space path loss. It's omnidirectional loss that the textbooks write about, but everything has gain at these high frequencies. So you're able to make up for the omnidirectional frequency loss, f squared, by the antenna gain on both the transmitter and receiver. And that's what massive MIMO really is going to do. It's going to be creating higher gain channels that pick off particular reflections, particular paths, and are able to make links so that you have parallel fiber optic like wireless links all going between the transmitter and receiver in different spatial angles. And this work by Nokia shows that even with the realistic channel conditions, with overhead, with imperfect coding, with cyclic prefix, you could start getting to a terabits per second really in 10 gigahertz channels or less as you get more and more orders of MIMO and massive MIMO. So massive MIMO is going to allow us to really achieve some of these big data rates. And why do I believe we're going to be able to get that times 1,000 capacity over the next 15 years? Look at what's happened in the US cellular industry just over the last 8 years. From 2010 to 2018, this is from the Cellular Telephone Industry Association's annual report, traffic is going up 50 to 80% every year, and they've had a 73 times capacity increase in the US cellular network in the last 8 years from 2010 to 2018. And that's just for 4G. That's just the rollout of 4G. That's before small cells. That's before millimeter wave with much wider channels. That's before massive MIMO. So we have these huge multiplier opportunities that are coming to 5G and are coming to 4G LTE just in the last year or two that never existed in the wireless industry. They're going to make this 73x over the past 8 years become something closer to several hundred X. So we're going to start going from gigabits per second to hundreds of gigabits per second to terabits per second over the air, mobile communications easily over the next decade. And this should be very compelling. And the FCC in the US and Ofcom and other countries realize this, so they're starting to open up spectrum now all the way to 3 terahertz. So for the first time in the US, there's frequency allocated up to 3 terahertz. So we're moving from the millimeter wave, 24, 28, 73 gigahertz, now all the way up to 3 terahertz. And today in the US, you can get 21 gigahertz of unlicensed spectrum up to about 250 gigahertz. It's available today. People are making products. And this is what we wrote in the 2019 paper we believe will happen. Wireless cognition, we believe that you'll have robotic control with this near real-time human computation, fleet control, drones, robots, autonomous vehicles, and even the human experience. We believe somehow there'll be human to human with computer-assisted real-time experience that we can't even envision today. Plus the sensing part of the tricorder will be able to use spectroscopy and detect and sense our world, build maps about our world, see in the dark because of the imaging, as I'll show in a minute, and of course communication and position location. When you check some of those videos, you see that one of the applications of the tricorder was to detect the exact location of objects or things or aliens. And there's a funny clip that you'll have to go back and look at. We can do this, and we will. So let's look at the spectrum today, just above 100 gigahertz out to about 275. The blue shows you these frequency bands that have been made available by the FCC, and these 3 bands have also been made available now in England through Ofcom. And these green are the International Telecommunications Union spectrum allocations that are right now available for co-primary, fixed and mobile. So you see there's huge amount of bandwidth. And this is just out to 275 gigahertz. We also have these gray areas where these are forbidden zones by the United States and also by ITU because they're satellites. These are satellites that are sensors. They need to be protected from emissions from Earth because these sensors are very, very sensitive. They're cryogenically cooled. They're in space. They're sensing the moisture from above the atmosphere. They're up at several hundred kilometers. And this is the path loss in dB for a typical slant path that is a satellite that's up above Earth. And what you can see is if the satellite's above Earth, there's huge amounts of attenuation. Thousands of dB, that is satellites that are on the horizon, won't see energy from Earth because of the troposphere attenuation of these frequencies. There's a lot of attenuation due to the atmosphere when you get above Earth, when you get and you try to go through the troposphere, the first 6 miles, first 10 kilometers above Earth. So there's this natural attenuation of satellites that are on the horizon. But when satellites are directly above Earth, any radiation from Earth could very easily interfere with these very sensitive sensor satellites. So that's a big concern of the satellite and space exploratory industry. And you need to make sure there's enough guard band so that when mobile happens at these frequencies, we don't interfere with those sensitive satellites and don't encroach on them. That's an exciting future area of research. But here's why I say the world really doesn't understand the channel yet, and hopefully everyone here in this conference does. The whole world's been below 6 gigahertz where you have virtually no attenuation. Even rain doesn't affect you. You know, you're fractions of a dB over a kilometer. But look what happens when you go up higher in frequency to several hundred gigahertz, even out to a terahertz. Check out up to 400 gigahertz, sea level dry, or even with moisture. It's the moisture that attenuates. Even with moisture though, look, you're only 10 dB per kilometer out to several hundred gigahertz. 10 dB per kilometer is only 1 dB per 100 meter, which is the radius of a small cell. So you only have 1 dB less loss in the channel in standard atmosphere than you do at sub 6 gigahertz. This is amazing. And even going out to 700 or 800 gigahertz, 100 dB per kilometer may seem like a lot, but that's only 10 dB per 100 meter small cell, the radius of today's small cells that are being built out for 5G. So 10 dB is easy to make up with additional antenna gain. You could have 5 dB on each end of the link. That's not a lot of gain to put into a directional antenna to overcome the loss. So this should bust a myth that frequencies attenuate terribly. It's only if they're omnidirectional antennas do they attenuate. If you have gain on both ends of the link, there's virtually no attenuation up to 400 gigahertz and very little attenuation even up to 800 gigahertz. Amazing. And rain, once you solve the rain for frequencies at say 50 and 60 gigahertz for today's 5G mobile, you solve the rain all the way up to a terahertz because there's no additional rain loss once you go above about 100 gigahertz. So engineering today's 5G millimeter wave small cells for rain will build in for the next 20 or 30 years the small cell design and infrastructure for 6 and 7G as we go up to several hundred gigahertz and we get these massive bandwidths. In fact, you can see here that rain, atmosphere, and free space, yeah, they don't go many tens or hundreds of kilometers, but they are very comparable to what we have today in cellular for 1 or 2 kilometer links. This is great news for the wireless industry. It means all the hard work being built out for the small cell revolution and the 5G millimeter wave band will carry us all the way up to several hundred gigahertz. So we've been studying how propagation works at these sub-terahertz frequencies. We've done a very massive study on our campus at NYU during COVID to measure the coverage and the links and the antennas and the number of multipath and the channels. We've looked up to 180 meters, and the students have even looked at what a satellite would see. What a satellite would see, here's a satellite receiver, a surrogate satellite receiver on the roof looking down, and we rotated antennas on the ground as if they were mobile users trying to keep their energy on the horizon. What happens if the radiation goes up towards that surrogate satellite? What kind of interference you have? And we've published these recently, but the bottom line is this millimeter wave link will work. It'll work just like 5G. We're going to go up to several hundred gigahertz. The small cells being built out for millimeter wave will hold us for the next several decades. That's wonderful news. And that means as we get these wider channels, the ability to do wireless cognition, the ability to transmit data rates close to human real-time processing computing speed will become viable. Now, we talked about the sensing part of the tricorder. Many of you know, and there are some good papers here about terahertz sensing and imaging. These frequencies, terahertz, are unique because they're between millimeter wave, which is being now deployed for cellular, and infrared. So almost light-like. So images can now be rendered by scanning these very directional antennas in space. Machine learning can provide classification of what's received, what the received energy is doing, and what the profiles of scattered returns do over different frequencies. So you can imagine a mobile phone, this device operating at many, many different bands in the sub-terahertz and terahertz region, compiling different signatures and being able to do machine learning or classification and crowdsourcing to build knowledge of what the channels are like and what the environment's like. Spectroscopy really just means looking at electromagnetic energy and how it interacts with matter. So by using wide bandwidths and different frequencies throughout the sub-terahertz and terahertz, we're going to be able to detect resonances, measure moisture, detect the presence of certain objects, find allergens in our food, determine if there's a smoke or fire. And we'll also be able to see behind walls, because while millimeter wave can penetrate and infrared can't, terahertz operates between those bands. So if we have a map of the world, as I'll show you, we can actually start looking behind walls and start doing imaging, thermal imaging for line of sight, and then using the radio property of terahertz to figure out what's going on in places we can't see with 9 line of sight. So first thing, for this sensing capability, these super wide bandwidths are going to enable super fine resolution components, great resolution and propagation times. And you can even resolve propagation times as a trigger without having a huge amount of bandwidth. But the point is, you're able to resolve spatial resolutions of centimeters with a fraction of a nanosecond. And we've already seen decimeter level ranging achieved at 300 gigahertz in line of sight. I'm going to show you some work we've done where we've got centimeter level accuracy in non-line of sight with just one base station. I'm so excited about this work. And so we have this wide bandwidth, and then we also have the ability to use narrow beams. Going higher and higher in frequency means, as you can see here, the antenna half-power beamwidth becomes smaller and smaller as we get a larger number of antenna elements, getting 1.5 degree beams with 64 by 64 element arrays, which you can build in terahertz circuits. It'll be a challenge, but people are working on it. The point is, you can get these very, very narrow scanning arrays and start doing some amazing things with sensing. And the FCC is even promoting this. We're starting to get less than 3 meter horizontal and vertical positioning. We've written some papers about it and shown how by using maps and using ray tracing. Remember, this phone is going to have the ability to compute several trillion computations per second. I mean, that's amazing. We're going to be several trillion computations per second. So doing ray tracing and real-time rendering and things we never thought could be in a handheld device, we'll be able to do that. And we'll be able to create maps on the fly. So by having a map or building a map through sensing, we can then start to predict what the environment is and start doing a matching, a machine learning of what's happening in our channel vis-a-vis what the physical environment is. And we're starting to do this. We've built some prototypes. We built a ray tracer at NYU. We call it NYU Ray. And what we're doing with the ray tracer is we're looking at an algorithm which we call MAP-AT. MAP-AT is map-assisted positioning with angle and time. These are the two things we get by going up to terahertz. We get high resolution of angle of arrival, and we get great temporal resolution of time. So we're doing map-assisted positioning with angle and time. I won't go through the details, but it's really a remarkable way to look at what you receive from a transmitter. If you know where the transmitter is, if you know what the environment is, you can basically backtrace every possible multipath component in the map and determine where you are by what multipaths you received versus what the map gave you. This is very promising. On today's computing, we can implement this in a microsecond to 50 microseconds. If you do parallel processing, worst case with 4 multipath components, up to 10 multipath components at terahertz. You can do this in 14 microseconds. That's today, and that will increase. So we're going to have real-time sensing on where we are and mapping of the world in determining exact position location. Here's some of the work we've done recently using our channel sounder, operating with a 1 gigahertz bandwidth up at 140 gigahertz with typical power levels that you'd see in a handset, estimating Gaussian error of timing and angle, which we think are conservative. But doing conservative measurements, the students have gone out and looked at this in indoors and outdoors, and have found that we're able to get 5 centimeter position error with just one base station and a crude map of the environment. So we're able to get centimeter level accuracy for localization. And with that accuracy, we could then start predicting energy that goes through walls, behind walls, to then determine what's behind the walls and start doing imaging actually behind the walls. We're working on that. So this is remarkably encouraging indoor. We went outdoor. We also looked at extended Kalman filtering. They can help smooth when you have problems in the channel. And this is kind of the relationship of the error, angle arrival, and time of flight. We're using those two key things, and we're able to determine from the measurements where we are in the map of the world. Going outdoor, we went along this path. Here's the transmitter at 142 gigahertz. We went along this track. You can see there's non-line of sight here. So we lose the strongest signal. It's all reflections. And even then, with 142 gigahertz, typical 1 gigahertz bandwidth, transmit power of 0 dBm horn antennas, we're able to get a pretty good accuracy. Here's where the non-line of sight was. It goes from 10 and 20 centimeter error up to about 40 centimeter error. And this is where you had non-line of sight. But that's just with one base station. So the bottom line is you get about 7 to 10 centimeters over the whole track in the outdoor environment. We've also looked at doing this for drones, flying drones. This will be amazing. People wondered, would drones ever happen? Sure, they will. And so we're able to get position errors within tens of centimeters with just one base station at 73 gigahertz. These are simulations, but over 100 meters. So imagine drones all flying around, not colliding with each other. They'll be able to sense this with the wideband channel and directional antennas. So some of this sensing, spectroscopy should be clear to you. We can do this. It should be clear to you. We can do position location. We're able to get sub-decimeter accuracy. We're just looking at one base station. You start merging base stations, start combining data, we believe it'll become even better. But communicating with drones, having a tricorder that can detect and sense and store. How many people remember the Jetsons cartoon in 1962 with all these people flying around in their personal hovercrafts? Well, that's what drones are going to be. So in 1962, the Jetsons, a famous cartoon, predicted we'd all have our own flying vehicle. And today we're talking about UAVs, unmanned aerial vehicles, and looking at connecting and sensing and predicting where those drones are. It's really going to happen. And let me leave you with this. The idea of cyborgs, that is part human, part computer, and this concept of transpecies, people who are somewhat machine, that's not so far-fetched when you start thinking about the human brain and its computation. Kevin Warwick wrote about this in 1996, Cyborgs, and Neil Harbisson had this antenna put in his brain in the early 2000s. He's a artist and a proponent of transpecies. It's pretty freaky to think about, but with terahertz and sub-terahertz, we will start reaching the ability with the computer itself to be able to process at human level speeds. And with one final thought before we go to Q&A, I'd encourage you, if you're really fascinated with this, take a look at this 1967 movie. I showed it to all my friends when I was in Austin. They all fell asleep, but I had to wake them up for the last 3 minutes of this movie. It's a fascinating movie. It was made in the free love days of the hippie days of the 1960s. This famous actor, James Coburn, he was an unknown at that point, but This movie I watched, somehow I was a kid, I had no business watching it, but this movie, The President's Analyst, I think motivated me to a career in wireless. And then the Star Trek communicator and tricorder even amplified that interest. And I think I'm not the only one. So hopefully this shows you that wireless cognition, the ability to use wireless and the terahertz, sub-terahertz channels is going to happen. It's going to happen in the wireless industry. The physics are there, the channels there, the work we're all doing is there, and it'll be an amazing future. With that, I'll stop sharing. I'll thank my industrial affiliates. Go check out this final link. I'm not going to try it, but it's a nice way to end this talk. And I just want to thank all the industrial affiliate sponsors of NYU Wireless and the National Science Foundation who helped make all this happen at NYU. With that, I'll stop sharing and turn it over to you and see where you want to take it, Professor Kaiser.
Many thanks for this brilliant talk. Yeah, so you see, I'm still smiling because there were so many things from my childhood which I remembered. Yeah, meanwhile, the Star Trek. What I didn't know before is the story of Martin Cooper. Yeah, that he was motivated basically to invent the cell phone based on the tricorder from the Star Trek. And also I remember very well this Motorola first cell phone which you put off and on, yeah, which indeed looks like the tricorder, yeah, from Star Trek. So thank you very much for the really nice talk. Yeah, and let's say I look for the audience. Is there any question